Hello, community. So great that you are back. Yes, it's summertime and we're going to talk about cognitive AI, the latest in AI research as published today. And of course, we're going to talk about multi-agentic frameworks, of course. So let's start. Let's switch here a little bit our perspective. Multi-AI agent collaboration is something that is absolutely fascinating here to unlock the next level of intelligence. So let's talk about this. Now, we have here, if two agents here meet each other and everybody in there has its own LLM, you could see here the other one as a simple system, like a personal computer. And the agent just has to learn how to use a PC. You have an unknown UI and unknown apps, but no problem for our multi-agent system. The second case could be you really see another agent. But this agent has unknown training and unknown abilities, so you will have to explore how to cooperate with these agents for complex tasks. Or, and of course you have unknown MCP and A2A disclaimer, no? I mean, of course. And then we have a real complex self-evolution. Now the agent meets, if you want, a possible future self. And it says, how do I have to evolve to or perfectly configured for my next complex task, given here the craziness of this YouTuber who wants to push me absolutely to the limit with a complex self-evolution in a multi-agent system. So what is the latest research of today? So let's talk about the next frontier. And I know GPT-5 maybe is going to be released today by OpenAI, but I have to tell you, it is not about building bigger models. No. It is about something else. Maybe 3 points, to learn autonomously, to collaborate more effectively, and AIs that evolve their own architecture much further than we do currently. Learn autonomously means adapt to new unseen environments, and this is going to be paper 1. Collaborative effect is multiple AI agents can solve now new complex problems, because currently AI agents are only trained that they act here in solopreneur function, but not as team leaders. And we need an architecture code that rewrites itself. We have to modify the whole internal code structure of our AI agents. 3 new research papers. And from hundreds of papers, I selected those 3 because I thought, sitting at the beach, it might be interesting to have here a common look August 6, 2025. So let's start here with the first one, a simple PC system. So our highly intelligent AI agent has to learn how to use a PC. Couldn't be easy, we have an old-fashioned user interface and now a hyper-intelligent agent that works on, 1000 NVIDIA Blackwell GPUs. So what could go wrong? So how do you enable an LLM an agent here, of course, to act effectively in a dynamic multi-step environment where the state changes based on its own actions? And we only have more or less one instrument, and this is reinforcement learning, yeah? So therefore we say, listen, we formulate the agent world now as a partially observable Markov decision process, the classical way, and its multi-agent equivalent. Guess what? We have a decentralized pump. So we go in the classical way. Here we have paper 1, August 6, 2025, Shanghai Tong University, Shanghai Artificial Intelligence Laboratory, and the Chinese University of Hong Kong. A highly interesting paper about self-evolving computer use agents with autonomous learning from experience. So here you have a little agent. You give full access to your computer, to your PC for your financial data, your health data, your communication data, your email data, everything that is you. And you say, hey, just show me how you can self-evolve. Isn't this beautiful? We can do experiments here in computer science. So what we need, easy. We need here a world state model. I have a separate video on world models and why we need world models here. And we go with a curriculum generator that simply generates increasingly diverse and challenging tasks. And then, it reinforced learning. So the only thing we have to care about is the agency policy, how to update this in an optimal way through an experimental learning. And you say, hey, that sounds interesting. Now, an AI that has access to all of my data on my PC, and the AI should do now some experimental learning. Are you sure we want to do this? Absolutely. Because we use here a known tool for the optimization, GRPO group relative policy optimization. So you might say, hey, what could go wrong? Now, let's have a look. In the easiest case, you have something like Photoshop, and the AI has now to learn all the function of Photoshop. So either you give it here the PDF manual, or you say, hey, here you have online access, just play with it. And now a human might take a week, 2 weeks, I don't know, a month to understand all the function, what you can do in the combination of all the functions. Well, let's say we only give 10 hours or 50 hours to our AI that is connected to 1000 GPUs, and you just let the PC burn to the ground. We could have here a look at the flow diagram, but it is rather simple, so I just give it here in a semantic linguistic form. We have a self-evolving pipeline, an autonomous system design with 3 LLMs that interact now. Now the first is easy. This is the actor model. This is our classical policy pi theta, the agent that interacts here with our software graphic user interface. Let's say it is Photoshop or whatever app you have, doesn't matter. It is our student that learns this simple interface. Then we need a judge. No, this is the world state model, here fine-tuned vision language model that acts here, if you want, in the function of a judge. Full trajectory of screenshot and action and provide step-level feedback. Of course, we need here reinforcement learning, a denser reward signal. This is crucial for the learning, and this is more or less the only job that this fine-tuned vision language will perform. And then we have something like our teacher, no? So we have a third LLM, let's call it a curriculum generator. So it analyzes now the agent's success and failures and consults here a software guidebook that it maintains here in its memory. And based on this, it generates here a new set of more challenging tasks. So it increases simply the system complexity with more challenging tasks. So the learning process is now a simple, beautiful loop. The curriculum generator proposes here at first a simple task, like open a file, or paint the background in blue, or whatever. And the actor LLM attempts now to do this, fails, and the world state model judges now here the entire attempt, labeling each step as success or failure. And then we have a policy update. This is the learning happening now. And it's a simple 2-part process. We use the GRPO or multi-agent GRPO to reinforce this. We have failure action, and we use adversarial imitation. This is the specific loss function for adversarial imitation. And otherwise, it's just the final loss, a combination of both loss function. And yes, we could do it much more complex. I would not say intelligently, but yeah, this is the simplest case. Now let's benchmark this, and you see here a Q1 2.57 is, but it falls down the more complex it will get. A 72B vision language model is already better. Look at this. But then if we go GPT-4 Omni and other huge models, you see, oh yeah, they can hold up, and they can provide here the reward function for the evaluation of the precision. And it is all about, you have to go to reward model here for the reinforcement learning. Self-evolution of a graphic user interface agent is therefore rather simple. Think about this. In whatever application you want to learn, it doesn't matter at all. For examples here, you have different phases, a very low complexity, a medium complexity, and a rather high complexity, or I have to say, set a breakpoint at line 14 in the current Python script and start debugging it is not really a high complexity. But you see, you can learning slowly increase, and you have a self-learning process, and all the parameter that you have in your benchmark says, yeah, the system is learning something. Is it the optimal way? No, of course not. But at least we're doing the steps in the right direction. So there we have it. Old computer apps, let's call this here apps. And we have here a 1000 GPU artificial intelligence system that says, my goodness, I have to learn these stupid things, how to use all of this. Yeah, it's easy. So this is now able to evolve into a role here of a real specialist for individual software platforms, software you have forgotten how to use it or whatever. So AI can do this. This is simple pattern recognition. AI is a pattern machine, no problem at all. You can go across multiple software environments. Great. But let's make it a little bit challenging, no? Not just a simple user interface with apps or PC. Let's go here with another agent. Now we agents that have an unknown MCP and A2A disclaimer here, no agent card or anything at all that describes what it can do, what is its ability, what was its training data set. Just they meet somewhere here in the unknown, and now they have to figure out a way how they can cooperate. Like two persons, no? Meeting somewhere in the desert. Now interesting, because up until now, if you have here a little agent, you know, all the training we did with agents was, also if you have the orchestration agent in a multi-agent system, it was trained to be here a single fighter on its own. We don't have extensive training data set for 2, 3, 4, 5, or 7 agent interaction sets. We don't have the training data. Yes, we can have synthetic data, but you know the complexity we run into this if we have this. So therefore the question is, what can we do and how can we optimize this? Now you see, here we have 3 agents that meet here on a path, a trajectory, and they will have to cooperate, work together to improve their performance. And the question is, how they gonna do this? How they gonna achieve here a self-evolution, a self-coordination, and then we can go on to higher complexity tasks. So here's our second study. This is here by the Northeastern University in Boston, Massachusetts. Hello, beautiful. August 6, 2025. You see the second paper of today. LLM collaboration with multi-agent reinforcement learning. And now we have something beautiful. Now we have this multi-agent GRPO optimization here, and we have a look in technical details how we can implement this. And yeah, of course, as I told you, we have here a DAG pump. Here you have again every definition if you're not really into this. And of course, this is here our optimization problem. And if you're not familiar here with a little bit of mathematics, never mind, I have a specific video where I explain all the AI mathematics to you in simple terms, the easy way. Now, multi-agent GRPO is rather simple from the idea. No? You have here the magic. Instead of a single rollout at each turn, they generate now a group of G joint responses from the team of the agents. Then they receive here a joint reward for each of those G responses. And the advantage of a specific joint action G in the group is now not calculated against the learned value function, but relative to the average performance of the group itself. Is this the best way forward? No, but it's a single step in the right direction, and therefore I show you this new study. I kind of like it. Give you a simple example. Imagine you have to write something and you have 2 agents. The first agent is here, the agent for the very, let's say, overview structure. No? And the second agent is more of a technical agent that writes here, you know, the methods and everything. Great. And if you would have not a multi-agent GRPO, they might produce here stylistically jarring or repetitive context, you know. They would write maybe chapter 1 and 4, and the other one would write chapter 2 and 3, but it would not be one coherent style. So what we want to achieve exactly with multi-agent GRPO is a joint reward function here for reinforcement learning that measures here explicitly the structure, the coherence, and the style consistency. And of course, the job is to find a collaborative sweet spot where the detailed writer learns to use transition words that smoothly follow the core idea laid out by the writer that focuses here more on the overview paper, maximizing here together their joint reward functions. Yes, of course, if you are not happy with my words here, you see a very simple schema of the publication. Let's do another paper here, and they give here an evaluation exactly on this example where you have 2 agents that writes now a scientific paper. So the first agent outlines here the research background, and the other agent writes here the proposed methodology and the experiment. And great, and you want to have that the whole paper looks like one person wrote it, a coherent and consistent representation of the new knowledge in style. And of course, they performed here a lot of experiments. Here you have for the efficiency and the quality and the return and everything. You have here, just look at all half rows here at the lines. You have it for a single model, a parallel generalization, and the new multi-agent GRPOs from the authors. And you see in bold, oh yeah, they achieve here a quite interesting jump in the performance of this. And it was funny they did this on a simple RTX 5090. So you still can do research here with consumer GPUs. The authors tell us, yeah, we think that the LLM collaboration here that is so important to train one core of an agent, the LLM, not as a single fighter, but as a team leader or as a team player. This is the next step we have to do. We have to do cooperative multi-agent reinforcement learning. Currently, we have problems doing here the optimization, understanding here all the complexities here or the error prolongation here, how we do here the optimized configuration of aligned reward structure. And they currently do this in coding and writing. Imagine you have to write some real complex code and you don't use one agent to the code. You use multiple agents. Now, it turns out all your agents that you use currently are already trained and optimized to be a single player agent. And they miss out on the benefit of being a team player and utilizing here the strength of being in a team. This would be the next step. So real interesting fascination here by this paper. This is the reason why I show it to you. And of course, the third paper. The third paper is now that this thing here is aware of itself, aware of its uniqueness, and it asks now itself, like looking in the mirror, what is the complex self-evolution I'm capable of if I think about it? What could I implement by myself? So I don't know if this is the future form of AI or if this is the future form, or should we go with a humanoid form of AI? This is now something. Let's talk about the self-evolution of AI. And of course, we have a new paper. This is now by Carnegie Mellon University, absolutely fascinating, University of Bristol, Clemson University, Portland State University, and they have a new system. They talk about, if you want, about the intelligent personal assistants like Siri 2 or whatever you have, a cognition-centered framework for proactive, privacy-preserving, and self-evolving LLM agents or AI agents, intelligent agents, published today, August 6, 2025. And this is now a lot of fun because they have here a complete new framework with 2 new agents. So let's have a look what Carnegie Mellon University is here proposing to us. They say, hey, Siri was not so really developed in the last years. Imagine what Siri could be as an individual personal assistant. And they say, how do we design this? And they say, hey, we have an idea that we combine the cognitive architecture of the LLM agent with its particular task. And we will ask, what about here a self-evolving AI system that can rewrite its own code base? And they have here the new term of a cognition forest, a semantic structure designed to align here the cognitive modeling with a system-level design of the architecture itself. Real nice. So we have now a combined view at software and hardware architecture, and the AI more or less should be able to optimize both structures. They present here Galaxy, this new framework that supports here multidimensional interactions here with the environment, so really an agent per definition. And we also have this personalized capability generation here as a Siri 2 or whatever you call it. So they say in the minimum case, we need 2 cooperative agents. And what a coincidence that we just looked at multi-agent GRPO optimization for the learning process. We can use this immediately for those 2 agents and not let them train here in singular action environments. And the 2 agents are Khoury, a cognition-enhanced generative agent, supports both responsive and proactive skills. And Kernel. Kernel is an unfortunate name because kernel means already something. So I say kernel X, a metacognition-based meta agent that enables here self-evolution. I know it's not, hey, that sounds great as a marketing, but is there anything from a scientific point of view? Absolutely. But sometimes the most interesting idea have a very simple background. Look at this. They say, hey, we have a user, let's call it whatever. And I have a deadline approaching that says the user, I read more paper this month. I use here my native language. So I have to translate each and every paper that I have from every language here in my mother tongue. And it starts and it's like, please translate this paper. Translation happens. Translate the other paper. And you see the AI notice here a particular pattern in the user suddenly is emerging. And AI comes back to the user and says, hey, you translated a lot of paper recently. Do you need a specific translator space now? Should I build you something that is optimized for these new tasks that I discovered in your human behavior? And the human says, oh yes, please, I need to translate. Thank you, Siri 2. I need to translate your PDF files and convert them into Markdown files. And now this AI will say, well, of course, I built a new agent. Done. And then you have to have the intelligence, and this is now the second agent if you want, Quora, that you have to integrate this in the human behavior, in the flow of actions. So now it's drafting your plan when to activate the system, let's say at 10 a.m. in the morning when the student wakes up and starts to work. And they have a specific sequence of action, launch the translator space, request user feedback, and then you have here the dashboard and simple drag and drop PDF file from any language in here and will be translated in your mother tongue. And you will have here a specific representation that you can ask for. So you have a further individualization here that Siri 2 might be able to do. And yeah, Apple, the new next conference is coming up within weeks. So let's have a look. Now, if you would like to see this from a little bit more of a technical thing, yeah, absolutely, but nothing specific here. They did it, they built it, what are the results? Let's have a look, how good is it? Now, if you have different benchmark like Agent Board or here anything else, you see you can go with a GPT-4 Omni, you can go with an O1 Pro, with an Opus 4, a Sonnet 4, Gemini 2.5 Flash, this is nice, a QN3, this is nice, and then they have the 2 Galaxy models. And as you can see, especially here at the Agent Board, you have here in bold here the best performance. And if you compare here some of the performance increase that they achieve for some specific benchmark, this looks really interesting. Some dedicated workflow infrastructure here, given here specific needs of the human. Very short summary, what is a cognition forest? Integrates here the cognitive architecture and the system design by itself, forming here closed loop mechanism. Again, you see it's always a loop of alternating optimization. So very simple presentation. Cognition drives the understanding. No? This new framework builds an understanding of the user needs. The cognitive triggers now reflection. This new framework assesses where in the current framework capabilities, let's say it has access to your computer. So we connect to the paper 1 of this video. Do we have software that fully covers the user need? Yes, use it. No, let's build it. Let's identify the user requirement, the unmet requirements. Point 3, reflection guides now the system design. This new framework translates now the unmet needs into a new system design. Maybe I just have to write, or this AI has just to write here a new command line, or you have to generate a new app. You have to integrate this into your workflow, so you can optimize autonomously your system capabilities. And this design now reinforces cognition. So this new introduced structured create now additional cognitive pathways, a new app that you can use, or sensing capabilities, which in turn strengthen and optimize the original cognitive architecture, help here the human student to optimize the human learning process. So you see, interesting how this now interplays here. And I would say here, the cognitive architecture and the new system design, the flexible system design, the AI system design, and now co-constructive objects. Or if you want to have it here in the word of the authors, they design here Galaxy, here a new framework that initially possesses here proactive skills, privacy preservation, and a self-evolution, because they also say cognitive architecture and system design of LLM agents should be deeply integrated and form a reinforcement loop. So this was our first paper, this was our second paper, and our third paper. And I think it's absolutely fascinating that they really form together something. I think they have here a convergence. All recognize that the learning from experience via the reinforcement learning is the path forward. We have nothing else. From group relative policy optimization, I think I've seen 23 versions now from old GRPO and whatever we have now. Never mind, it's always the same idea, the same implementation. Second, I think if you view it here together, this paper now, no, you could say that multi-agent GRPO provides here a concrete algorithm for inter-agent collaboration, since it optimizes now the learning experience here as a team of AI agent in a way that has never done before. Then the second paper provides a framework here for agent environment learning. If you think that environment is simply your PC with your programs, with your app that you have, and an autonomous skill acquisition here. So this huge AI learns here each and every of your personal computer functions here autonomously. We had a look at an example here of AutoCAD or something else for photographs. And finally, the new framework provides here an overarching self and agent to user architecture for persistent, evolving, and personalized agents that are coming up that will substitute a lot of the human work that we do on a computer, on our apps, in our interaction pattern. I think agent will change significantly how humans interact with computer over the interface of an artificial intelligence. Any thoughts left? Yeah, I still have thoughts. So as you see, 3 papers, 3 ideas here now condensed to the max. First was reward design. World state models use step forward, designing a reward function that captures here the nuanced human preference. Still a central problem, still an open problem. Then we had the meta problem here. If we could use here some curriculum generator that generate here higher, more complex question and tasks here given the time. But the next layer of abstraction is how do we build agent that can design optimal learning environments for other agents. So you see we have agent to agent learning is now in the focus of artificial intelligence. And finally, as agents become more and more autonomous and can modify their own code, like we had to look at this framework here, how can we ensure that their behavior that should help the humans in their interaction, in their evolvement, how can we ensure that their behavior remains aligned with the human values? Very interesting question for the future. Why not subscribe? And I see you in my next one.